Right, so let's have a look at these questions then for this first drill. What you've got to do here, find the current. So what do we need to know? Right, we need to know Ohm's law, which tells us that voltage is current times resistance. But of course we need I, so rearranged I equals V over R. So that's what you need to remember, and then you just plug the numbers in. V, which is 3.64 times 10 to the 3, over R, which is 5.7 times 10 to the 6. Before we do this on the calculator, just a good idea is to have an idea whether we expect a large or a small answer, so we know what to expect when we do the calculation. Dividing a voltage of that by resistance of that, what would you expect, large or small current? Small current, yes, because that's about 5.7 mega ohms, 10 to the 6. So do that on the calculator, and we get did I hear you right, Gareth? Right, yeah. Okay. Is that how you'd leave the answer? No, okay. So what would you do with it, Gareth? Okay. So how far would you bring that decimal point forward? Remember, in engineering notation, we tend to move in threes, so 3 or 6. Okay. And then what would we put at the end? Times 10 to the minus 3. Amps, thank you. Don't forget the unit. Is that how you'd leave the answer? Is that an appropriate accuracy? So what would you do, Nizar? Sorry? Okay, so, and you'd get... Yeah, amps, yeah, that's either of those will do, Nizar, but that really wasn't what I was driving at. Is that an appropriate accuracy? No, remember it's not the decimal places we're after, it's significant figures. How many significant figures in there? 3 significant figures would be appropriate, yeah. Remember the golden rule is it's either the same as the least accurate figure, which is this one, look, which is only 2 significant figures, or maybe one more. So perhaps I'd go to 2 or 3 significant figures, certainly not more. How many significant figures at the moment? 4. So I'm going to round down to 2 or 3, and that would be up to you. So what would it be to 2 significant figures? You sure? Right, 640 times 10 to the minus 6 amps, or 0.64 times 10 to the minus 3. So that would be to 2 significant figures. So what do we do at the end? 2 significant figures, yes. 2 significant figures. And to 3 significant figures? 639 times 10 to the minus 6 amps to 3 significant figures. Because we've used engineering notation, which goes in threes, what could we do instead of writing 639 times 10 to the minus 6 amps? Microamps, right. 639 microamps to 3 significant figures, or 0.639 milliamps. I think that you should be very comfortable with doing things like this. If not now, very soon. You need to work on it, okay? That's a very typical calculation. Right, number 2. So again, we've got to remember something. What is it we've got to remember? SOHCAHTOA. Which one are we interested in? Because we know the adjacent, well, the adjacent is what we're interested in, and the hypotenuse we know, so it's this one that's going to tell it to us. And so what do we now do? Yeah, I think so. But so what? To write the formula down, cos of theta equals adjacent over hypotenuse. That's the rule, isn't it? So we're after the adjacent. So you're right, Gareth. The adjacent would be the hypotenuse times the cosine of theta. So that's going to be 15 times cos 45. 6.1. Okay. Lastly, is that an appropriate accuracy in the light of what we've just been saying? Yeah, probably two significant figures, so 11. You might think to yourself, we're losing some accuracy there. 10.61 is going to 11, but bear in mind, we can only be as accurate as the number we put in. You know, just because the calculator's saying 10.61 doesn't mean it is that accurate. That's the accuracy, the 15, isn't it? Yeah. Next. Right, yeah. What you mean, added the frequencies together and divided by 4. Yeah, no, it's not right. Exactly right, actually. Times the frequency by the midpoint of the group. The midpoint of the group will be, for this one, yeah. All right, okay, yeah, 15.5, that's an interesting one. That's fine, but what I normally do is I look at the last one in that previous column, which is 10. So what's halfway between 10 and 20? 15. I would have used 15. So rather than going from what's halfway between 11 and 20, I would go what's halfway between the last one in the previous group and the previous group. So 15, 25 and 35. But if you've used 15.5, you're going to get and it's always a problem, you know, how to count, where do you put that midpoint? But I tend to use that idea. I suppose it takes into account the fact that here we're assuming the whole numbers, but actually this group could contain anything beyond 10. So 10.1, which makes 10 a better one to use rather than 11. So once we've got them, that means the frequency, I've got 4 of those, 8 of those, 3 of those, and 1 of those. So I've got to multiply them together. So fx 20, what's that, 4 30s, 120. That's right, isn't it? 25, 75, and 1's 35 is 35. Now you add them together to get the sum of fx to 250. Take your word for that. Yeah. And then what do I need to divide that by? The sum of the frequency, right, which is 16. So the mean is the sum of fx over the sum of f 250 over 16. Which is 15.63. Is that an appropriate accuracy? Okay. Certainly not 4. So 2 significant figures, yeah. What's going on? And which one you pick would depend on, you know, what the data is. What is it actually? We don't know that. So the accuracy of your final answer would depend on all sorts of things. Last question. If I were to put into autograph that function a, y equals ax squared, what would I expect it to see? Right, and what shape would the curve be? Okay, so let's go to autograph and type in y equals ax squared. Y equals ax squared. Hit OK. And look at it. Okay. If I change A, and we're sort of moving now on to the sorts of things we're looking at today, so focus in. If I change A, what effect will it have on the curve, do you think? Right. So let's try it. Let's go to the constant controller, change A. I'm multiplying x squared by a bigger number, so therefore it's going to increase more quickly, so it will go up a bit. If I reduce A, but notice the position of the curve remains unchanged. Okay. What happens if I type in y equals minus ax squared? If I make A negative, what effect will that have? Right, it will switch the curve upside down. So if I make A negative, it goes the other way. So minus ax squared will go there. Note, when x is 0, I've plotted ax squared. Remember, when x is 0, the whole thing's 0. So it's always going to go to the origin, this point here. Okay. What about C? What would you expect that to look at? What effect will adding a B have? Yeah, because I'm adding a constant, aren't I? When x is 0, what does y equal? No? Y equals b, yeah. When x is 0, this bit's gone, so y just equals whatever value b is. So in other words, the curve should cut the y-axis at b. Guys, okay? So if I change the function to y equals ax squared and add a constant term b, then by default it sets the constants to 1. So it shifted the curve up to 1, look. So if I change b, then that makes the curve go up and down, okay? But doesn't change the shape of the curve. So which of these curves does that look like? Which shape is the curve? It's negative, so it's going to be D. B minus ax squared. Okay? So D. Okay. I'd like to just you to let me have those so I can have a quick scan at them. I'll give you them back if you want at the end of the session. So what's the aim for today? There's two things I want to look at today. I want to look at standard deviation. What does it tell us and how do we calculate it? And that is towards the first assignment I'm going to give you to do. So I'll give out the required questions for that today, and then next time I see you, which is next week, I'll give out the assignments if you have had to go at the required questions. That's a very straightforward thing to do, so it's a nice easy let into the units. It's an assignment you should be able to do next week and then hand me in the week after that without any problems at all. So that will be the first of 4 or 5 assignments done, okay? and then we'll have a break, and then I'll look at carry on our discussion about graphical representation of formula that we were just looking at a second ago, and how we can use that graphical technique to solve simultaneous equations. So that's the plan for today. So finding the standard deviation and what it tells us. Here's a set of data. I'm going to play around with this data now, so you might want to just make a note of this little set of data here. So I want us to find the mean for this set of data. What do? We need a further column to the right here. What will that be for? Fx. So I'd like you to find the mean of this set of data. And so I'll leave you just a few minutes to calculate that. Generate the fx column, find the sum of fx, sum of f, and then the mean is going to be, as we've done already, sum of fx divided by sum of f. So we find the mean, and 4 significant figures is appropriate because if you look at the data set that's gone in, x, 4 significant figures. Now, when you do a statistical study, there's normally 2 figures that you quote to represent your set of data. One is the mean, which represents the data. That's sort of a midpoint, some sort of average. And if you look at that average, 34.53 is roughly in the middle of our data set, which goes from 34.42 up to 34.6. So that's the mean. The other piece of data that we're interested in is something called the standard deviation, which gives us an idea of how spread out the data is. At the moment, we know the mean is 34.53. But without access to this table of data, we've got no idea how spread out the data is. If this was a mean age, say, of 34.53 years old, well, is our data set, does that include children that go right down to 4 or 5 years old, and adults up to 80 odd years old? Or is it a much smaller, narrower band of people? We need a figure that will tell us something about how spread out the data is, and that's called the standard deviation. And what it does is it tries to find the mean of the deviations. The mean of, by the deviations we mean the difference between each bit of data. Say the highest one here is 34.6. What's the difference between that and the mean? I take the mean away from that to find it. So what I do is, it's an estimate, it's an attempt to try and subtract the mean from each of the bits of data and then find the average of all those deviations. So what we do is we generate columns to allow us to do that. The first column we generate is one where we subtract the mean, which we've just found, from each of the bits of data. So I have another column out here, and there'll be about another 3, I think, off the top of my head, but allow yourself room for about another 3 or 4 columns. So the first column we want to generate is x, which is our data value. So the first one is 34.42 minus the mean, which we just calculated. So x minus the mean. So I will just pause for a second while you subtract the mean from each of these values for x. So 34.42 minus the mean, which we've just calculated as 34.53. Yep, you're going to get negative numbers and positive numbers because some are below the mean and some are above. Okay, so we've got the difference between them. Some are negative, some are positive. Now, if you imagine that this distribution is a nice even distribution, and we'll talk more about this in a minute. So this represents a distribution starting the frequency up the y-axis, so frequency is gradually increasing then dropping away to 0, and somewhere in the middle here is the mean. In theory, you've got just as many bits of data on the left as you have on the right. So if I were to just add these up, I'd end up with a value of 0, and all that tells me is that the data is roughly evenly distributed, which is useful but doesn't tell me anything about the spread. So what I need to do is to get rid of that negative sign effectively. We could just get rid of the negative sign, but what we actually do mathematically is square it to get rid of the negative side. So the next thing to do is to take our x minus the mean and square it. So we need to, square that, and that. Whenever you square a number, a little tip here, whenever you square a number, it's always going to turn out positive. So I wouldn't bother putting negative 0.1 in. I would just put 0.11 in and square that. Yeah, just square 0.11, square 0.03, and so on. So, think about what we've got here now. We've got rid of the negative signs. Remember what we're after. We're after a number that's going to give us an idea of what the average of all the differences is. Well, the x minus x bar column, this column here, is the differences. We squared them to get rid of the negative side. So to find the mean, we've got to basically add them together and divide by the number we got. But remember, if we look at the frequency column, what this means is we've got 3 of these 34.42s. So we've got 3 of these 0.0121s and so on. So we now need a column where we multiply each of these by the frequency to get the total difference. So the next column, and this is the last column we need, is a frequency multiplied by x minus the mean squared. So take each of these values, 0.0121, and multiply it by the frequency. So now we've got the frequency multiplied by each of the differences squared. The squaring is there to get rid of the negative side. So this figure, 0.0363, gives us an idea of how far away each of these values, 34.42, is from the mean, and taking into account the fact there's 3 of them. So we're now after the mean of these. How do you find the mean? You add them all up and divide by the number there are. So we're after the sum of this column, fx minus the mean squared. So we add them together. (0.06560) to get that. Thank you. Okay, 0.0656. Now, to find, we're almost there, now we're after the figure. If I divide the sum of fx minus the mean squared by the sum of the frequency, I get this sort of mean value. And it's called the variance. So the variance, VAR, is often the abbreviation for variance. Variance is the sum of fx minus the mean squared over the sum of f. So we can calculate that now. That's going to be 0.0656 divided by the sum of f, which is 15. We did that earlier. Sorry, Gareth, 0, 0. Yeah. Right. And we might at this point say, okay, 4 significant figures, so that'll do to 4 significant figures. all we do now is, the final step is, if we think what we did to get rid of the negative sign, we squared. So at the end, we square root to get rid of that effect. And that gives us what's called the standard deviation. So that, and there's a symbol we use for standard deviation that we've come across before, this sigma, and that's the standard deviation so it's given the letter sigma, and that's just the square root of the sum of fx minus the mean all squared over the sum of f. So in other words, we just square root the answer we've got for the variance, and we get the standard deviation, which is 0.066. Done. That's the standard deviation. So we've got 2 bits of data now, okay, for this data set. Let's go back to the original data set. We've now got 2 pieces of information about this data. Remember what the aim was. Here's our data set. We've got these first 2 columns here represents our data set. We've now got 2 figures. One represents the data, that's the mean. And then the other number represents the spread of the data. So the mean for this data set, the mean is 34.53, and the standard deviation is 0.066. And it's common to quote those 2 figures from a data set. In fact, statistically, if you were doing some statistics for the firm that you were working for, the mean on its own is generally considered to be a reasonably useless statistic without some sort of idea of what the spread is, the standard deviation in other words. So you'd always quote those 2 figures. What we need to do now is just to think about what this information is telling us. So I'll just look at that now, okay? Now, I don't want you to write this down. You can always print this page, or I'll give you a chance to write it in a minute. Let's just have a look at it. So for a normal distribution, so a normal distribution is one that's normal. Lots of things behave normally. In other words, if I were to plot the data set, like the one we've just been looking at, certainly when you've got a lot of data, you get this familiar bell-shaped curve, which is called a normal distribution. So this is a normal distribution. And because many things in nature behave normally like this, in other words, the data is spread evenly about the mean, we can often end up with skewed data as well. So there might be some sort of bias, which means there's more above the mean than there are below. So you can get skewed data, but often, without this sort of bias that's been introduced, you get these normal distributions. And this curve is very well understood mathematically. I won't bother to write it down. I used to be able to remember it, but I could soon look it up, what the function is that describes this curve. But the point is that it's been found. And if you think back to the calculus that we did last year, if I know the function that describes this curve, I can integrate to find the area underneath the curve. We did a little bit of that, which means I can find out how much is under each part of the curve. And that's the sort of thing that people then do with this statistical information. They can find the area under the curve, which tells us a little bit about the probability of a piece of data, for example, being at a certain place in this data set. And so it's found that very accurately the standard deviation actually describes pretty well exactly 2/3 of the data set. So if we look at this normal distribution here, and we've got the mean in the middle, let me just get the mean in the middle here, which is this point, I then find that actually 2/3 of the data lies within one standard deviation either side of the mean. So this particular bit of the distribution here, that's described in here, I won't shade it in because I'll destroy the diagram. In fact, I can do if I do this. So if I sort of, that bit of the data set there is 2/3 of the data. So if I've got the standard deviation calculated, I can say with a lot of accuracy, if it's a normal distribution, that 2/3 of the data lies within plus or minus one standard deviation of the mean. So 34.53 plus one standard deviation plus 0.066, 34.53, which is the mean, minus 0.066. If I work out what they are, I can say with a reasonable accuracy that 2/3 of the data I've got lies within that range. And the other parts are outliers that we might ignore, these other bits of the data. So, for a normal distribution, that standard deviation tells us something about our data. If you were in a firm and you were, say, it was some sort of manufacturing process which was generating thousands of machine parts, for example, the statisticians there would find the mean. What's the mean size of these things we're making, which we might be trying to target that. But beyond that, what's the standard deviation? So therefore, 2/3 of my data is going to be, or my machine parts are going to lie within this range. Okay. So that note, if you'd like to make it, tells us something about the standard deviation. I can do, yeah, but if you want to make a note of it, there it is. You can print it out if you want, Gareth, because it'll be on the website. If you want it with your notes, I'll just pause while you do that. Okay. Here's another data set. Let's have a look at it. What's the difference between this data set and the one we've just been looking at? It's grouped. So therefore, we take the midpoint of the group. So the first thing we have to do is find out what's the midpoint of the group, which I've given to you. So that's the only difference. We need a value x that represents the group, and then we're given the frequency. What I would like you to do now, I'm going to give you 5 or 10 minutes or so, is just to generate the further columns you need and then calculate the variance, the standard deviation and the mean for this data set. So, I mean, I've written down the answers. I think that's when I did it. That's roughly what I got. So, I'm hoping you can get it around about that. And I've just been sort of talking to Colin, and if I'd come up with this answer, you want to know it's right. I mean, that's the problem with statistics is you're adding up loads of numbers all the time. There's bound to be errors. You know, if a group of people added up a whole column of numbers like us, for example, I can guarantee we wouldn't all get the same answer because somewhere along the line there's going to be an error made. So that's normal. So, but you ask yourself, 21.92. That's roughly in the middle of the data set, so that seems reasonable. And if I remember what the standard deviation is telling me, it's telling me about 2/3 of the data lies within plus or minus one standard deviation. So if I add 0.65 to 21.92, I get about 22.5. And if you look at the data set, 22.5 is within this group here, so that seems reasonable. If I take 0.65 away from 21.92, I get about 21.3-ish. And again, if you look at the data, 21.3 is in this group here, so about 2/3 of the data. Yeah, that looks like a reasonable answer. Okay. So we can now find the standard deviation for a normal set of data and for a group set of data. And the assignment is going to ask you to do that, okay? And that's a shame because I forgot to put the... So you might have missed all that. If we think back to our aims, we've looked at the standard deviation idea. Now I want to just think a little bit more about these two, particularly that graphical representation of a formula and using that to solve simultaneous equations. It may be that we don't get to this last aim or we only just touch on it. Next week we'll focus on that in much more detail. Actually, as a reminder, next week, if you make a note for yourselves, we won't be in here. I went down to the library. We'll be in the LRC upstairs in the HE study area. So we can use the computers and get onto autograph so we can start thinking about this graphical technique for solving functions. So then I can set you going on some problems when I need to go. Yeah, we'll meet up there next week. So 8:30, make a note, please. Two things, remember. One, it's a 8:30 start. Or not 9:15, and 2, we're in that HE study area, not up here. In the LRC, you go up those stairs that are in there, and there's that room off, yeah, with the glass doors. In fact, I booked that for the next 4 weeks, so that's where we'll be. Okay, so let's look at graphical representation of functions. I'm going to be using autograph to look at these things. So next week you can look at these notes just to remind yourself how to use autograph to do this sort of work. Here's a function, a formula that we can think of as a function that relates the volume of a cylinder to the radius and the length. So there are 3 variables in this function. So a variable is often, or invariably, represented by a letter. Pi is the only thing in here that's not a variable. That's a constant we all know, about 3.142. But the other letters in there are variables. V, the volume, R, the radius, and L, the length. They're variables, meaning that they can change. So if I change the length, that's going to affect the volume. If I change the radius, that might affect the volume. I might want to keep the volume constant and see how the radius and the length vary. Imagine we were in a firm. So if you were in a firm and you had to get some sort of cylinder, it had to have a fixed volume. And so we can have different lengths and different radii. So the volume would be fixed. And I would want to plot the function that would represent how the radius changes if I change the length with a fixed volume. Or I might have a situation where the cylinder has got to fit into a certain space, and it's got to have a fixed length. So therefore, L is constant, and I might be interested in what happens to the volume of this thing as I change the radius. Or the last situation might be if it's got to have a fixed radius, it's got to fit into a particular aperture. So therefore, I can see what's the relationship with the volume and the length. So there are 3 variables that can change. And the variables are represented by these letters. Generally, we change or control one variable and then observe another and keep the remaining variable constant. So in this previous one, 3 variables, I might be interested in how the volume changes with radius, so I'd keep the length constant, and so on. Does that make sense? It's a sort of scientific method, isn't it? If you've got more than one variable or more than 2 variables, you keep one of them constant and then see how one changes with the other. So we have the controlling variable, the thing that we can change, and that's called the independent variable. So I might be interested in how the volume changes with the length. So I change the length in nice even steps and note what the volume is at each stage. I'm controlling the length, so that's the independent variable. And I'm observing what happens to the volume, so that would be the dependent variable. And all other variables would be made constant. So That's important, and I think you probably talked about this before, the independent and the dependent variable. So I'll just pause while you want to make a note of that, if you want to make a note. So, how does the volume change with the radius? We're interested in how the volume varies with the radius. So, there are my three variables. Which of these is the independent variable? We're interested in how the volume changes with radius. The independent variable, the one we're changing, radius. The independent variable on a set of axes always goes on the x-axis. So if we go back to here, the independent variable goes on the x-axis always. And the one that we're observing goes on the y-axis. So if you're asked to plot a graph, invariably you put the one you're controlling on the bottom axis, the x-axis. If you're wondering which goes where, the controlling one goes on the x-axis, the one that you're observing goes on the y-axis. So in this case, the radius is on the x-axis because we're changing that in nice easy steps generally, and then we're observing the volume, and so which is the dependent variable. The volume, so that goes on the y-axis. And what do we do about the length? Right, we keep that constant. So, in autograph, I would type this in. Remember, the original formula is volume equals pi r squared L. Whoops. Volume equals pi r squared L. So, if I wanted to plot this thing on autograph, then I would call the volume is the dependent variable, so that will be y. So what do I type into autograph? Y equals pi x squared L. And autograph recognizes any letter I put in other than x and y as a constant. So L. That's what I type into autograph. So firing up autograph. Let's close that. Start a new page. Incidentally, on this autograph program, if I just do this, there's a glitch with the program, and I think we're going to try and buy a new one in. But so if I just expand out the graph to its maximum size, it goes really weird on the right-hand side here. So to get round that, instead of expanding it right out, have it like this, and then just sort of pull it out until it starts to go off at the end, and then just drag back. So that will give us a nice even axis. Not an ideal solution, but until we get the updated version, that will have to do. So we're familiar with using this thing. So if I want to type in the function, enter equation, and I'm going to put in y equals pi. It recognizes the letter pi as being pi, so there it is. X squared. Remember, we can either hit x and then the squared here, or if you hit x twice, it gives you x squared, so xx will do it. And then I can type in the letter L to represent the length. So I type in y equals pi x squared L, literally type that in, hit OK, and I get a graph of how the volume changes with the radius. It's not straight, which I think probably we would expect it not to be, because it's y equals pi x squared L. So we can do the normal thing. I'm really only interested in the right-hand side as the volume increases. Generally in engineering, we're only interested in positive values of, certainly in this case, positive values of the radius. So we're not interested in negative radii. So we can drag the whole thing over to the right. And then we can, if I want to try and see this particular bit of the graph on the right-hand side, I could do with zooming in on the x-axis. So if you zoom in on the x-axis, then you see the graph start to stretch out. Zoom in again on the x-axis. Perhaps I should have done that before I moved it to the right. So there we go. Okay, so we can now, if that's not enough, I want to see what happens as the radius gets bigger than this, then I can zoom out. So I can put a zoom box in, or I can zoom out on the whole thing. And again, zoom in on the x-axis maybe, and then drag it over. So there's things you can do with this thing to get the graph to look like you want it to look like. And this is showing you how the volume of this thing changes the radius for a fixed length. By default, the program sets the constants as 1. So until you put in a value for the constant, it will set it at 1. So at the moment, this is for unit length of cylinder. So let's say the cylinder was 15 units long, whatever the units are we're using, we do that. And then that would, of course, change how the graph looks. So let's zoom in again. Now, we have a situation where I can read off exactly what the volume is for a series of cylinders, length 10, or 15 rather, wasn't it? Radius of 0.2 units, 0.3, 0.4. What's the volume of this cylinder? Look across, and there it is. So we can picture the function. If you want to put this into your assignments, just as a reminder to you, that's what I want. So I hit page, copy page as bitmap, and then I can go to Word, or in this case I'm going to go back to my notes here, insert a blank page, and paste it in. And there is my plot. And so now I can label it up. So this is a graph of volume equals pi r squared L, where the volume is on the y-axis, the radius is on the x-axis, and the length equals 15 units. It's fixed. So that's a constant, and we've now got a graph of volume against length that we can read off. Okay. How does length vary with radius? How does length vary as we change the radius? What would I set the radius? Which would be the dependent, which would be the independent, which would be constant? How does the length vary with radius?
Would the length be dependent?
The dependent, so would that be x or y? Good. Which would be the independent? And volume constant. Okay, so what would I type into autograph if I was interested in how the length varied with the radius? Remember the original function? But what am I going to type into autograph? Well, is the volume my y? No, it's not, is it? The volume is constant, so I'm going to leave that as v equals right. Okay, I just replace the letter with the particular variable that I'm interested in. And so now x is the independent variable, so I'm changing the radius. I'm changing the radius here and seeing what effect that has on y, which in this case is the length. So I'm seeing how the radius changes the length. So that's what I'm going to type into autograph. V equals pi x squared y. And then the autograph will ask me, either I can put this value in straight off into the formula, or I can put v equals and then just change v as using a constant controller. So let's go back to autograph. Close this page, start a new page. Enter equation. V equals, it won't let you put a capital letter in, so small case v equals pi x squared y. Hit OK. And there's the graph. Now, an interesting function to look at. Okay, this is the function. Again, what's on here? It's the x-axis is the what's x in this particular example? Radius. So as the radius changes, what happens to the length if the volume is constant? So positive radius on the left, so only interested in positive, not the negatives. So let's just get the thing to look how we want it. So let's zoom box in on, say, this bit here. And then copy pages bitmap, stick that into the notes. So there it is. So this is radius. This is volume. No, it's not. This is length. And we're plotting volume equals pi x squared L. So the volume is constant. That's 1. Does this look right, this function? The volume's got to be constant. Think of it from right to left. As the radius gets smaller, what's happening to the length? Increasing. Does that make sense if the volume's got to remain constant? Yes. Okay. As the radius gets smaller, thinking of a cylinder down here, then to have a fixed volume rather, as the radius gets smaller, it's got to get longer and longer, hasn't it? What's happening here? Yeah. But what happens as it approaches 0, Tom? What value will it have at 0? Yeah, it can be infinite, and it can never reach it. And so if I'm going to have a fixed volume, this graph approaches 0. And so that's a limitation of this model. You often get these sorts of things. It approaches infinity. As one variable approaches 0, the other variable approaches infinity. And that's common to see. So that sort of makes sense. Okay? Again, for a fixed volume, I can read off what length I require for a particular radius. Okay. Just pause this a second. How does length vary with volume? What I want you to do, and I'm going to just pause this for a second, is write down what you would put into autograph and then sketch what you think the function would look like. Okay? And then we'll look at it. So the original function, I'm interested in how the length varies with volume. So what am I going to put into autograph, Tom? Basically, you're rewriting this function, but deciding which is your x and which is your y, Tom, and which is constant. No, not rearranging the formula. How does length vary with volume? I'm changing the volume, so is that the dependent or the independent variable? Independent. So what will that be, x or y? Independent. X equals pi. Is the radius a variable or is it constant? So r squared, so therefore L must be y. Right, Tom? That's what I type into autograph. So that means if we look at this, pi r squared is constant. that's not going to change. So if I plotted a graph of x equals pi r squared against y, what would I expect it to look like? A straight line, yeah, because x and y are proportional to each other. So if I put this into autograph, I should get a straight line. Close this, start a new page, enter the equation. X equals pi r squared r, and then hit the squared, times by y, and then hit OK, and there's my graph. And as we anticipated, we get a straight line. There. Okay. Again, we can zoom in on the bit we're interested in. It all depends on what we have here as to what we call as how we zoom in or out on this graph. If I'm interested in, remember, x is the volume is x. So at the moment, the graph only goes up as high as a volume of 6. Well, I might be interested in higher values than that, and that would determine how I zoom. But let's say this is what we're after. So again, we're not interested in negative values of volume, so I can drag it over there like this. Page, copy page's bitmap, and then let's stick that into here. And there's our function. So we're plotting volume along here, and we're seeing how that affects the length up here. For a fixed value of r. And again, we could use autograph to change the value of r by using the constant controller. At the moment, it's set at 1. So useful things, and we'll be using autograph quite a lot over the next few weeks and maybe a month or so to look at functions. Any questions on that and the use of autograph? Okay, I will be giving you some questions to have a go at. What I want to focus on though now is one particular use of these things, which is to actually plot more than one function on the same set of axes so we can see where they intersect, and that means that's where the solution to two equations can occur. So if we think about two simultaneous equations, there they are, 1 and 2, we can solve those algebraically. We did this sort of thing last year. Any remember what sort of thing you do to try and solve these things? Good, yeah. You try and make x or y the same. So I might multiply form equation 1 by 2, so I get 10x in both. Yeah, that's right. And then eliminate that and find y, and then once you've done that, you can find x. Okay? We'll have a go at that in a sec. But we can also do it graphically by literally plotting that function and plotting the second function and see where they cross. Where they cross would be where the solution is. So I'd like to have a go at that. But before we do that on autograph, I want to see whether or not we can solve it algebraically as a reminder from last year. So I'm just going to pause this for a second. Remember, the start point might be one way. There's more than one way to do this, but one way might be to multiply equation 1 by 2, so they both read 10x. So have a go at solving those and find x and y. So the first step might be to multiply equation number 1 by 2, and that's a shorthand way to write that, to get this. So let's call that equation 3. So equation 3, take away equation 2 to make sure we get positive values. 10x minus 10x is nothing. 8y minus y is 9y equals 62 minus 26. So now we can find y straightforwardly. And once we've got y, we can plug that back into one of the original equations to find x. So this means that y equals 4. Now I'm going to substitute into, say, equation number 1. So I'll rewrite equation number 1, but instead of y now I'm going to write 4. So 5x plus 4 times 4 equals 31. So now I've got a little equation to solve. 5x plus 16 equals 31. So subtract 16 from both sides, leaves me 5x equals 15. Divide both sides by 5, x equals 3. So x equals 3, y equals 4, but I would check by substituting into 2. So check in 2. Always check. So rewrite 2 with putting the values in. What is equation 2? 10x minus y equals 26. So 10x, which is 10 times 3, minus y, which is 4, does in fact equal 26. So, I know I'm right. Actually, you'd be surprised in an engineering scenario, simultaneous equations are not that uncommon, because we often get a situation where we've got a couple of unknowns and a couple of situations like this, and we can then find them. Unfortunately, it's not always the case that they're nice, straightforward, linear equations like this. They might be more complicated. So instead of trying to solve them algebraically, following a method like this, we would just plot the functions using some graph plotting software and find out where they intersect. So let's try using autograph to do that very thing. So let's fire up autograph. Start a new page. So now I just type in the equations. What's the first equation? Okay, that's the first one. We would expect maybe a straight line because it's linear. There's no powers of x or no powers of y. Can't really see it very well, so let's just zoom out. And there's my function, okay? And now I enter another equation and put the second equation in, which is? Of course, the equations you have might not be x and y. Autograph only recognizes x and y, so you just got to assign x to one of the letters and y to the other letter. Hit OK. And we get the other. Now, the beauty of this method is, first of all, you can find out straight away whether or not there is a solution. It might be in an engineering scenario that there is no solution, particularly if one of your functions is a curve. You can well imagine a situation where you get a curve for one of the functions and a straight line for the other function, and they don't actually intersect. And so then you would conclude, without having to go to a load of algebraic manipulation, that there is no solution to these two simultaneous equations. So that's one of the real powerful uses of this sort of technique, using a graphical solution. So straight away we know there is a solution. All I've got to do now is use autograph to zoom in on that solution and find my values of x and y. So I use the zoom box tool. Here. and I can see where they intersect, and already we can see that it's exactly intersecting on a point. X equals 3, y equals 4. So we read it off from the graph. X equals 3, y equals 4. One of the limitations of this, so one of the advantages is that you can determine whether there is a solution, and if it's a couple of complex functions, then you can do it very quickly. The main disadvantage of this method is that your answer only determines on how well you zoom in. It doesn't give you an exact answer. In this case, we can see that it is, because I set it to be nice, easy numbers, but often it isn't. So algebraically, if you were to go through the algebra, you'd come up with an exact answer. However, this method, you can just keep zooming in until you've got as much error as you want. Yeah, you've got it to enough significant figures, but it doesn't give you necessarily an exact answer, which can be a disadvantage. So a graphical solution, once you've got the graphical solution again, maybe we would like to insert that in. And so I can now put it into the notes. Okay. So graphical solution. Oh dear, don't like the look of that very much. What's going on here? So a graphical solution would be here, and we can zoom in and get the results. So we look down to get X, and across to get Y. And we have to zoom here. So there is an error involved, or an accuracy issue, depending on how well you can zoom in. The fact that they intersect tells you that there is a solution, but the actual accuracy of the result is determined how well you zoom in. Okay, pause that there for a sec. So the aims, we're looking at standard deviation. Okay, there's two things that we quote. So two things that we quote when we're talking about statistics. What are those two things, Gareth? One of them's on the board. No? That was a joke, wasn't it, Gareth? Standard deviation and? No? The mean. Mean and standard deviation are quoted. What does the mean represent? Right. Only a few more minutes. What does the standard deviation tell us? Yeah. Yeah, there's the spread of the data. Anything in specific? What does it tell us specifically? Good. 2/3 of the data lies. No. Ben? Right. 2/3 within, yeah, but that's okay. We're reviewing. You've got it written down within one standard deviation, and sigma, often used for that, of mean. So how do we do that? How do we get that standard? How do we get this range? What do we do? Work out the mean, work out standard deviation, then to get the range. No. To get this bit, the spread of the data, add it, and subtract it, Connor. Add this standard deviation to the mean to get one side, subtract to get the other side, and then you've got 2/3 of the data within those two. Yeah? Okay. If I've got a function, Elliot, okay, with lots of variables in it, and I want to investigate that function, what do I do?
Keep one variable constant.
Okay, so investigating functions. Well, before we do that, what do? Yeah, we keep some of the variables constant, but what are we interested in? Right, so we identify dependent and independent variables. Which axis does the independent variable go on? X. Identify X and Y, independent and dependent variables, and then, Elliot, yeah, all others constant. Last thing, if I want to use, Gareth, if I want to use autograph and these idea of functions to help me solve simultaneous equations, one advantage of autograph. Yeah, quick and easy to do for complicated functions. Another advantage. Tells you if there is a solution straight away. Good, Ashley. One disadvantage. Not as accurate as solving algebraically. Yeah. Okay. We'll call it a day. And I will see you next Friday. Don't forget, 8:30 over in the HE. Thanks. Cheers. Thank you. So,